Do I want to say this now? No, I'll come back to that later. Okay. But remember those groups, okay? They're going to come back later. So it's this slogan that there's the non-positively curved behavior out of Fn, or I could do this for the mapping class group as well, is largely, not entirely, but largely captured by this, the action on homology. And there's this other bit which we're going to study by other means. Okay. So that's a significant difference between lattices and between mapping class groups and out of Fn. Okay? Lattices only have finite quotients, lattices in higher rank, whereas these other groups have these other interesting infinite quotients. Okay, so what am I going to do? We're now going to have a short section where I'm going to talk about actions of mapping class groups and out of Fn on non-positively curved spaces. I'm just going to state some theorems without proofs and see how they fit into this picture. And then I'm going to try and actually have a section with a proof in it. I hope we get that far. I'm interested in maps between the three classes of groups we have. Now, what do I mean by that? Well, I might mean, so our three classes of groups are, once again, SLNZ, or SLNZ, sorry, or more generally lattices and semi-simple Lie groups of higher rank, mapping class groups, and out of Fn. Now, when I say maps between our three families of groups, I might mean maps within each class. Okay, if I take out of F7, how do I map that to other outer automorphism groups? How can I have maps from one mapping class group to another? But I also might mean maps from lattices to these things, maps from these things to lattices. Okay, I'm going to state theorems of each of those types, but the one I really want to get to and say something about the proof, it illustrates the principle best that I'm trying to talk about, is a theorem I proved with my student Rick Wade a few months ago. I've been wanting to prove for ages. So if gamma is a lattice, an irreducible lattice in a connected semi-simple Lie group G with real rank at least 2, then every homomorphism, so superrigidity result, you want to say that these lattices can't act in an interesting way on free groups. Okay? So every homomorphism from gamma to the outer automorphism group of a free group has finite image. So I want to sketch a proof of that because it uses several deep theorems by other people, and I want to explain how they all fit in. Okay. Everyone got that? So that's the main thing I want to talk about. Okay. So higher rank lattices can't act in an effective way on free groups. I should say for mapping class groups, the analogous theorem, exactly analogous theorem. So you also, higher rank lattices can't act on surfaces. The analogous theorem is due to, well, it's actually in a paper of Farb and Maser, but it relies on earlier work of Maser and Kajmanovic. And there's various other proofs of it, which I'm going to mention, and that goes back to 98. Okay, so that's where we want to go. But first, let's have the shortest. Let me just talk about actions of mapping class groups and out of Fn. How can they act on spaces of non-positive or negative curvature? Now, the mapping class group does have one interesting faithful action on a space of non-positive curvature, namely the Teichmuller space with its very Peterson metric. Okay, but that's not complete. That metric's not complete. But you can just complete it. Okay, you complete it. It's still a cat zero space. The mapping class group is still acting faithfully. Okay, so that's an interesting. Actually, it's a semi-simple action. It turns out every automorphism is either axial, so either translating along. It's either got an invariant axis or it's got a fixed point. Everything's either hyperbolic or elliptic. But it has large stabilizers. Okay, Dane twists will have fixed points in that action. Okay, so it's certainly not a discrete action. And, of course, both out of Fn and the mapping class group do have what classical actions on space of non-positive curvature, because you have the map from out of Fn to GLNZ, and this will act on symmetric space. Okay? So there are those classical actions of mapping class group, or you can act on the Siegel space, symplectic group. So there are those classical actions on space of non-positive curvature, but they're not faithful, of course. Okay? So how can these groups out of Fn and mapping class group act on other space of non-positive curvature? Okay? And somehow part of what we're trying to get at here is superrigidity. Okay, so what does superrigidity, Margulis superrigidity, tell you for SLNZ? Well, or other lattices in SLNR, it says SLN is shy. It's very shy. Or loyal, depending on your point of view. Okay, so it won't act anywhere. It won't act anywhere, let's say on any non-positively curved space, unless it can take its nice warm environment with it, unless it can take the whole of SLNR with it. Okay? That's the basic principle. Okay? It's really very shy. It doesn't want to go alone. It has to take the whole of SLNR with it. So if you try, for example, you try to map SLNZ to some other semi-simple Lie group, it says, oh, no, I'm really very shy. I don't speak the language. I'm not going unless I can take the whole of SLNR with me. Okay? So the morphism of the discrete group. Well, give it a few drinks. You never know what will happen. Okay, so to what extent do mapping class groups and out of Fn feel like this? Well, but they don't have an ambient Lie group to take with them. Okay? So it's not going to be quite like this. They're not going to be as rigid. So again, you've got this part of these groups, but the other parts might start doing something interesting. Okay? On the other hand, you hope that at least these groups remember sort of where they came from. They should remember, for example, something about the geometry of the Teichmüller space or out of Fn or something. Okay? So you expect some echo of rigidity, but not all of it. So let me just state a couple of theorems that go in that direction. So I'm not going to say anything about the proof, but this is really just to try and illustrate the extent to which I think it retains rigidity and the extent to which it loses it. So I've written these in a particular order for a reason. So for all actions of mapping class group or out of Fn on a complete cat zero space, action by isometries, of course. Oh, damn, I forgot to tell you something earlier. Let me tell you something and pretend I told you a lot earlier. Okay, when I was telling you something about some of the differences between SLNZ and mapping class groups and out of Fn, I forgot to mention something. So imagine I mentioned this a lot earlier. In the basic generators for SLNZ, okay, are the elementary matrices. Okay, things like this. Now, you might ask, if you take the cyclic subgroup generated by that inside SLNZ, is that more or less geodesic? Is that isometrically or quasi-isometrically embedded? And it's not, right? In any word metric in SLNZ, if I take a matrix like this and I start raising it to some high power, it doesn't get away from the identity as quickly as you expect. It only goes away like log k. Okay? So it's really distorted. These cyclic subgroups are really distorted. They're far from geodesic. But in mapping class groups and out of Fn, if you take any element of the group, called gamma, either of these groups, if it's got infinite order, then the distance in the group from the cyclic subgroup generated by that element will be a sort of quasi-geodesic. Okay, it will grow linearly. The distance to the identity will grow linearly as you iterate it. That's not a trivial fact in either case. I'm not quite sure who it's due to for mapping class groups. I think probably it's Hammenstadt, and in out of Fn it's due to Emir Alibegovic. Okay? So this is really an important difference between mapping class groups out of Fn and SLNZ. In this way, out of Fn and mapping class groups are acting more like a uniform lattice. Okay? This would be true for a uniform lattice, but it's not true for non-uniform lattices. Okay. The reason I remember that I'd forgotten to say that is that I'm about to say something related here. Okay, so the mapping class group and out of Fn, they're acting on a complete cat zero space. Now, in the group, the cyclic subgroups are all undistorted. But whenever it acts on a space, for all Dane twists, those are the basic generators, remember, or that's for mapping class groups, or these other basic Nielsen generators, and I'll call them all delta. Okay. So those cyclic subgroups are undistorted, but when it acts on a cat zero space, it remembers that they're supposed to be like parabolic elements. Okay, so the translation number in the space of all of these elements, that is, you just see how far things are being moved. You pick your favorite point in the space, it doesn't matter what point it is, and you start looking at orbit, and you ask how geodesic is that orbit. It's not geodesic. Okay? These act like parabolic orbits. Okay? The translation number will always be 0 whenever you're acting on a cat zero space. So to that extent, it's sort of, this is just a statement about these abstract groups, right? But they remember sort of the geometry that they ought to be, morally speaking, they ought to be parabolic isometries, or they ought to be parabolic elements of the mapping class group. So let me just mention a couple of corollaries of that. See, why is this a useful theorem? Well, I won't spell it out, but this is going to tell you something about the representation theory of gamma, right? Because if you map to say SLNR or any it's mapped to SLNR, it's going to tell you that Dane twists and Nielsen generators always have to go to unipotents, okay? Because they have to have a 0 translation number when they act on the symmetric space. Okay, so this is going to give you some control over the representation theory of these groups. Another corollary is it says that if you get any homomorphism, this is relevant to the last section, if you get any homomorphism, say from a mapping class group from one mapping class group, say of a surface of genus G, to some other mapping class group, the mapping class group to some surface G prime, phi of a Dane twist, let's say roots of twists, will always go to roots of twists. Okay? So somehow they remember that they're supposed to be Dane twists. This isn't a hard corollary once you know this, but I don't have time for it now. It requires saying more words than I want to. Okay, so somehow that's an aspect of rigidity that remains when you look at actions of these groups on non-positively curved spaces. Do I want to say this next bit? Maybe I'll skip the next bit. There are also fixed point theorems according to dimension, that these groups can't act on spaces that are too low dimensional. But I want to skip that for a moment and just ask a question that I'm continually bothered about related to this this comment about representation theory. So it's a famous open question about whether the mapping class group has a faithful linear representation. And you can use these sort of ideas to prove that it has no non-trivial representations at all up to dimension about root G. Okay, that's what I can do so far. But now, is it true? Does every representation of the mapping class group, the surface of genus G, say, into, let's say, SLDC, a finite image? There's nothing particularly special about the complex field here. You might ask this for any field. A finite image if D is less than 2G. Okay? I think this is a very reasonable conjecture. Let's see. Okay? So in dimension 2G, you get the symplectic representation. Okay? Maybe there's nothing smaller. Okay? And say at the moment, can get up to, instead of 2G, you can get up to about root G. Now, for out of Fn, there's a theorem like this. Okay? There's even a topological theorem due to myself and Karen Voigtman that says, in fact, if D is less than n, so the corresponding thing for out of Fn should be not 2G, but n, okay, because that's the dimension of the representation on homology. If D is less than n, then there does not exist any non-trivial action of, say, out of Fn, even by homeomorphisms, on Rd. Well, in fact, here you can have any acyclic manifold. Okay. So this is sort of a stronger version. And so the linear version of this is saying there's no representations below that dimension. But there's nothing at all below that dimension. I might point out, actually, this theorem is new for SLNZ. SLNZ, sorry, keep getting where I am. Of course, SLNZ, you classically know SLNZ has no linear representations below dimension n. But why can't it act by homeomorphisms on a smaller Euclidean space? Okay? And this theorem says it can't. But I don't know how to prove that if you take a torsion-free subgroup of finite index in SLNZ. This really uses torsion. Okay? So a flaw of this theorem is it doesn't extend to subgroups of finite index, okay, which in some sense is what one wants it to. Okay. Any questions from clearing this board? Okay. So there's a few comments about how these groups can act on negative or non-positively curved spaces. And it's in a constrained way, okay? And we don't fully understand it yet, but it's very constrained. They certainly don't want to be non-positively curved groups. Okay, let's say a few words about coarse non-positive, coarse negative curvature. Because there are interesting, now they're not going to be discrete, but there are interesting faithful actions on delta hyperbolic spaces. So for the mapping class group, so I'm afraid I'm just talking to people who know what these objects are for the moment. I don't have time to explain. So the theorem of Mazur and Minsky is that the curve complex is hyperbolic in the sense of Gromov, and the action, so this bit's really due to Bowditch, of the mapping class group is what's called acylindrical. Now, what does that mean? Well, what matters here for us is this curve complex is some simplicial complex, some locally infinite simplicial complex that's made up of curve systems. So a vertex in this complex is some curve system, like I was talking about before. And if two curve systems can be placed disjointly on a surface, right, then you join them by an edge, and that gives you a graph, and that's the one skeleton of this curve complex. And that's a delta hyperbolic space. Okay? Now, this business about it being acylindrical, well, you see, this won't be a discrete action, because the stabilizer of a vertex will be that part of the mapping class group which leaves this curve system invariant. And that will be some infinite subgroup of the mapping class group. In particular, it will contain the Dane twists. Okay? So the Dane twists will be elliptic. They'll have fixed points in this. But what this acylindrical forces is, there's an analogous condition which Latin Besfino and Koji Fujiwara have got called weakly properly discontinuous, right? What matters is that the pseudo-anosovs here, the irreducible elements, act as axial isometries, axial or hyperbolic or loxodromic. Okay, so there is an action of the mapping class group on a delta hyperbolic space, which isn't a discrete action, but it's sort of picking out. It's faithful on the pseudo-anosovs, if you like. It sees the pseudo-anosov part, the part with hyperbolic dynamics of the mapping class group. Okay, and one would like a theorem like that for out of Fn. There's a major step in that direction due to Besfino and Fein, which is that for out of Fn, and the fully irreducible element, that's one that doesn't have a decomposition. Right? I start saying by the elements of out of Fn are very complicated things. They might come in these blocks. Suppose it doesn't come in blocks. Okay? So in any fully irreducible element psi, there exists an action of out of Fn on some delta hyperbolic space, okay, which is like the curve complex here, in which this particular element is axial. Okay. Well, actually, you can do this with any finite number, but you can't do it. See, here, you got an action on a hyperbolic complex where all the irreducible elements at the same time are axial. Here, you can't do it. We can't yet do it for all elements at the same time, but you can do it for finite families. Okay. Now, why do we care about that? Well, we care that's a rather beautiful thing. But the consequence I want out of that today is that one could apply a theorem of a very recent theorem of Damany, Girardel, and Dennis Ossen, which builds, this is really a theorem in small cancellation theory. And I feel I have to use these words since this is a conference about negative curvature. It really uses Gromov's idea of mesoscopic curvature, okay, which is this wonderful idea where Gromov has a version, well, I should say Delzon's name as well, because he really helped to clarify this a lot. Gromov has a version of the Cartan-Hadamard theorem for hyperbolic spaces. Okay, now you think that's not possible. We all love the Cartan-Hadamard theorem for classic negative or non-positive curved spaces. You're passing from infinitesimal or local to global. But in a delta hyperbolic space, you have no local structure, so you can't have a Cartan-Hadamard theorem. Okay, but what Gromov points out with this mesoscopic curvature idea is that if you have a delta hyperbolicity up to a certain fixed scale, then you can go from that scale to global. Okay, so it's a medium scale to global theorem, a medium scale to global version of the Cartan-Hadamard theorem. And using that, these guys prove that if you've got a, let me just say it. So if psi is in the mapping class group, or it's an out of Fn, and if it's one of these irreducible elements, aficionados know I should be saying fully irreducible. I'm going to stop saying it in a second. So in the mapping class group case, that's a pseudo-Anosov element. Okay, in the out of Fn case, it's an analogous thing. Then there exists some integer, some power you can raise this element to, so that if I take the normal subgroup generated by that power of the pseudo-Anosov, now what would I love to say that is? Well, if I just take one pseudo-Anosov, or fully irreducible element out of Fn, you should think of those as like hyperbolic elements in hyperbolic geometry. Okay? They're axial things. We've got them acting in an axial way on a hyperbolic space. So if you take such a thing and you conjugate it, okay, a conjugate will go over there, you have north-south dynamics, and the classic ping-pong argument will tell you that that thing you first thought of and any conjugate of it will generate a free group. Except you may need to raise it to a certain power to make the dynamics work. Now this is like that, except we haven't just done it for one conjugate of this thing, we've done it for all conjugates at the same time. And the remarkable thing is you can make that a free group. Okay, it'll be an infinitely generated free group on those generators that you see. It is a beautiful theorem. Okay. And it's proved using these two theorems I talked about. Right. So suspect, ping pong might make you suspect this, but this is nothing like a ping pong argument. I need that because I'm now going to try, in the remaining minutes, you can either go to sleep or not, you can wake up or not now, but I'm going to try and sketch a proof of this theorem with Wade. Okay? So let me remind you what this theorem is. So you've got gamma in, well, it's a lattice, it's an irreducible lattice in a semi-simple Lie group. We'll just say SLNR. Okay, but it really works in any semi-simple Lie group of higher rank. Okay, and the theorem is, so for all homomorphisms to out of Fn, the image should be finite. Okay. So this has 3 basic steps to it. Let's say it relies on deep work of other people. Okay, so step 1, case 1, suppose there exists an irreducible element in the image. Suppose there's suppose that so you're mapping to out of Fn, okay? You're mapping to out of Fn. Suppose you catch one of these irreducible elements, a pseudo-Anosov-like element. I claim that can't happen. Well, why can't that happen? Because then you see the normal closure of this thing intersect the image of phi. What's that? Well, that's a free normal subgroup in the whole of out of Fn. I've intersected it with this image. Okay. Now I don't get the whole thing, but it's still normal and it's still free. Subgroup of a free group is free. Okay. So this is a normal free subgroup in the image of phi. So if I pull it back, so phi inverse of n is a normal subgroup in gamma. But we're supposed to know about normal subgroups in gamma. Either they're just finite, either they're finite and central, or they're a finite index. But this is not a finite index, because when you quotient out, you get a free group. Okay? So that actually is a contradiction. Okay? So that's, what I'm contradicting here is the Kazhdan-Margulis normal subgroup theorem. In the general case, or just the fact I started with up here, and if you've got a lattice in SLNR, then there's only normal subgroups, a finite and central, or a finite index. And we just constructed one that's neither. So that can't happen. Okay? So that does not happen. Okay? So you know that the image of your homomorphism to out of Fn. Can I have 2 minutes? Yep. You know that the image of your homomorphism doesn't have any irreducible elements in it. Now, in the mapping class, by the way, this gives a very short proof of the Barb-Kaimanovich-Mazur theorem, because in the mapping class group, if you don't have a pseudo-Anosov, you've got a subgroup of the mapping class group. If it doesn't contain any pseudo-Anosovs, then it's a theorem of Ivanov, quite a straightforward one, that there's an induction and then a theorem of Ivanov that says this argument together with some reduction theory in the mapping class group quickly proves the whole theorem. Okay? But the reduction theory for out of Fn is not so easy. Okay? You've got a subgroup of if you've got a subgroup of out of Fn that doesn't contain one of these irreducible elements, so what? Okay? What can you say about it? Well, there's another recent and very nice theorem of Handel and Moshe that sort of gives you the reduction theorem you need here. And it says this. So if you've got H is some subgroup of out of Fn, and it's got to contain no fully irreducible elements. Okay? So it has none of these pseudo-Anosov type things. Now, the technical definition of a fully irreducible element is an irreducible element, is something which leaves a proper free factor invariant. It's what you expect. Okay? It's got some subobject, a proper free factor of the free group invariant. And what they do is they go from the individual level to the subgroup level. So you've got a subgroup of out Fn containing no fully irreducible elements. Then there's some subgroup of finite index in H, so that H0 leaves the conjugacy class of some proper free factor invariant, up to conjugacy, invariant, where this is just some proper free factor. Okay? So it's some free factor of the free group. So it's somehow like a bit like a Colchan theorem. Okay, you get an invariant block, an invariant subspace. Okay, now that opens the door to an induction argument. Speed up here a little. So you've got this lattice, you're mapping it to out of Fn, you're now assuming it has no fully irreducible elements. Okay, so I let H be the image of that. So what Handel and Moshe are going to give you is a subgroup of finite index, which is going to leave some free factor invariant. Okay, so it's going to leave this free factor invariant. Well, that's going to give you an induced map to the outer automorphisms of L and to the outer automorphisms of L prime. Okay, so there's an induction on rank here. You know, you'd like to say that, well, you do know, by an induction on rank, the image of gamma, then this, or you've passed to some subgroup of finite index, so big deal, so what? The images here and here will be finite. But that does not mean that they don't generate an infinite subgroup out of Fn, unfortunately. Okay, so the induction's not easy. But what it does tell you is when you look at the action on homology, you'll have a finite piece corresponding to L. You'll have a finite piece corresponding to L prime. Then you'll have some other piece. But if that's finite and that's finite, that's a virtually abelian group. Okay, that has an abelian subgroup of finite index. Just think about it, it's not hard, I promise. Which means we've come up with a virtually abelian quotient of gamma. But gamma is a lattice in a higher rank Lie group. It doesn't have any virtually abelian quotients except for finite groups. Okay? So I know that was a bit quick, but I want to sketch how this Handel-Moshe reduction theory, an argument about homology, means that the image will be finite when you act on homology. But that wasn't a proper induction. Because I used induction that the image in out of something smaller was finite, but then I switched the action on homology. So what this actually does, what this argument actually does, is reduce you to the case that I really want to get to, the final case. What happens if you've got your irreducible lattice mapping to IAN, the kernel of the map from out of Fn to GLNZ? Okay, then you can't possibly detect anything with the action on homology, so what? Okay, so you're stuck with this problem. And this is an example of this philosophy I was trying to push, that, okay, these earlier arguments are really to do with negative or non-positive curvature, and they took care of that part of out of Fn. Taking care of this part of out of Fn requires a different mindset. It's in this world that I was talking about acting on free nilpotent groups, and using the technology that people like Magnus developed concerning the Lie algebra structure, for example, on these things. Okay, and so using those ideas, so this uses old ideas of Magnus and a Greek mathematician, Andriadakis, and then also Basson and Lubotsky have a nice paper on this. So using ideas coming from those, what we actually have to prove here is for all subgroups of IAN, that is the kernel of map from out of Fn to GLNZ, as long as this subgroup isn't trivial, there actually exists a map of this group onto Z. This group is indicable. Okay? Every subgroup maps onto Z. But lattices can't map onto Z. Okay? Higher rank lattices can't map onto Z, and therefore the image of this is actually trivial. So the only map from higher rank lattice to IAN is the trivial map. I'm sorry to have gone over. I'll stop. The unipotent part here. So, right, so by induction, so you think about how the image of gamma is acting on homology. So on this free factor, it's acting as a finite group, and on this free factor, it's a finite group. But there's this unipotent part. But because these blocks are non-trivial, this is actually a virtually abelian group. Right, and so since it's a quotient of a lattice, it's a finite group. Yeah. Yes. No, that's a very good question. I have absolutely no idea how to prove that. So it uses Smith theory, so you use the torsion completely. And in fact, that theorem is not true when you pass to an arbitrary subgroup of finite index. So in out of Fn, there's a subgroup of finite index which maps onto SLn-1 of Z. That's a construction of Grunewald and Lubotsky. And so you definitely can go down a dimension by passing to a torsion-free subgroup of finite index. And all the experiments seem to suggest you can only go down by 1 in dimension, but that's not a theorem. But you see, I don't know. So even for SLNZ, take a torsion-free subgroup of finite index and SLNZ. Now, it's probably true that it can't act by homeomorphisms on Rd if d is less than n. But I have no idea how to prove that. So now the homeomorphism group of Rn is so lacking in structure, even in the classical case. So take a torsion-free lattice in SLNR. Can it act non-trivially by homeomorphisms on a Euclidean space of dimension less than n? No idea.